In this lecture, we're going to talk about electrochemistry. And electrochemistry is the relationship between electricity and chemical reactions. So if you have some chemical reaction A plus B and it goes to, C plus D, and there are electrons that are transferred in that process, you could take those electrons that are coming out of the reactants or flowing between atoms and connect them to a wire. And that wire can go through something like a light bulb, shown here as just a resistor, and light it, doing electrical work. So you can take spontaneous chemical reactions, which we've learned about, delta G negative, for certain chemical reactions. You can take those chemical reactions that are spontaneous and going to happen, and electrons are going to start to flow, and use those electrons and that spontaneous reaction to do electrical work, like light a light bulb. This is how batteries work, designing a chemical reaction that's going to be spontaneous when you connect a wire. But electrochemistry is also about non-spontaneous processes that you might want to encourage with electricity. So maybe this reaction doesn't happen, but if you hook up a electrical source, you can encourage this reaction that otherwise is non-spontaneous to occur. And we can use this in things like electrolysis, where we can plate one metal onto another metal, like nickel plating or making things corrosion resistant, for example. So electrochemistry is all about chemical reactions that involve electricity. Maybe getting electrical work out of a reaction if it's spontaneous, or using electricity to drive what otherwise would be a non-spontaneous reaction. So before we jump into those applications, we're going to spend this lecture video really just studying the basics of charge in atoms and molecules and assigning oxidation numbers. So an oxidation number is something you'll sometimes see, if we had like a molecule of HCl, these are sometimes written above +1 and -1 to represent sort of where the electrons are spending their time in this molecule and the charge on each individual atom in that molecule. Now, when the molecule is neutral overall, like a neutral HCl, those numbers need to add to 0. And so let's just refresh some rules for oxidation numbers. Elements, if they're by themselves, like say it's just a solid iron atom, the oxidation number is 0. The same can be said for an element by itself, like H2 existing as a diatomic. It's just elemental hydrogen. The oxidation number is 0. Now, if it's an element that is existing as an ion that has a charge, well, then that charge is the oxidation number, 1+. Or maybe magnesium, 2+. The oxidation number is 2+. In molecules, like HCl we talked about, halogens will usually be -1. Fluorine, for example, is always -1. Oxygen in molecules, say like H2O, is almost always going to be -2. Unless it's hydrogen peroxide. In this case, oxygen's oxidation state is -1. Hydrogen is usually always going to be +1. So here in water, hydrogen is +1. There are 2 hydrogens, each at +1. So hydrogens are adding +2 overall. Whereas oxygen is -2. Those two add up to 0, as they should, because this is a neutral water molecule. In peroxide, hydrogen is +1. There are 2 of them, so that's +2 total, balancing the oxygen -1 oxidation state in peroxide. 2 of those for -2 total. Those balance each other out to make the molecule neutral overall. Okay, so the sum of the oxidation numbers equals the overall charge. Usually that's just going to be neutral, but sometimes you'll have charged things like SO4 2-, for example, where that might not be the case. Okay, so oxygen -2, almost always. Hydrogen +1, almost always. Halogens -1. Okay, elements by themselves, 0. So let's get some practice here assigning oxidation numbers to each element in the following compounds. Go ahead and pause the video here and try to assign for each element. So for example, for nickel and for oxygen, what are the oxidation numbers of each of those elements in that compound of nickel oxide? Pause the video here and take a minute or two to solve this. Okay, so let's first look at nickel oxide. Now, nickel as a transition metal can have a lot of different oxidation states, but we know oxygen is -2 pretty much always, unless it's peroxide, H2O2. So oxygen's going to be -2. There are 2 oxygens there, so -4 total. This molecule is neutral overall, right? There's not like a 2- up here or a 2+ signaling that there's some charge overall. So it's neutral overall. That means nickel must be +4, right? To balance that -4 of oxygen. So the oxidation number here on nickel is +4. The oxidation number here on each oxygen atom is -2. We can do the next one for copper. It's just a single atom of copper that has an ionic charge of 2+, so that is the oxidation number, 2+ or +2 for copper. Doesn't matter if you want to write this as +2 or 2+ when you're referring to the oxidation number. I tend to write them as +4, -2, +2, like that, but you will see it probably both ways. Let's look at the third one, NH4. Here, there is an overall charge. So we need to make sure that all of our oxidation numbers sort of add up to +1. Hydrogen we know is +1, and there are 4 hydrogens here. So that means my nitrogen here must be -3. 4 hydrogens each at +1 is going to be +4 total. So my nitrogen must be -3 such that these add up to be +1. The overall charge on this compound, right? So the answer here for NH4+, ammonium ion, would be hydrogen's oxidation state is +1. Okay, remember we're asked for the oxidation numbers on each individual atom of each element, not like the total contribution of all the atoms of hydrogen. So the oxidation number of hydrogen here is +1. The oxidation number of nitrogen is -3. Just to circle all the oxidation numbers here. Lastly, let's look at nickel hydroxide. We can go through each element. Oxygen, usually -2. Hydrogen +1. So overall, this OH is going to have a -1 charge, which we also know hydroxide is -1. There are 2 of these hydroxides overall. So there's a -2 charge overall here from the OHs, meaning that here my nickel oxidation state must be +2 since this nickel hydroxide is neutral overall. So nickel here would be +2, oxygen -2, hydrogen +1. Okay, now that we've assigned oxidation numbers, we're going to start to consider what happens from reactants to products. Do these elements, like nickel, go from a +2 state to a +4 state, or a +2 state to a +1 state, right? These oxidation numbers can change throughout the reaction due to the flow of electrons or the trading of electrons. One element might lose electrons, another element might gain those electrons. Okay, so we can assign oxidation numbers for the elements on both sides of a chemical reaction and keep track of what happens. If the oxidation number increases for an element, okay, that element is oxidized. So for example, if an element goes from +2 as a reactant to +4 as a product, that is oxidized. Now, this change in oxidation state is because it lost electrons. So oxidation is loss of electrons. If the oxidation number decreases, so it goes from +4 to +2, then that element is reduced. And we call that reduction, where reduction is the gain of electrons. Okay, so you're gaining negatively charged electrons. To go from +4 to +2, you have gained 2 negative electrons for that element. Okay, so reduction is the gain of the electrons. The oxidation number decreases because electrons are negative. Whereas oxidation, you are losing 2 electrons here. So you're losing two negatives, so the oxidation number gets more positive because you're losing those negatives. Okay. You can have a simple mnemonic to remember these definitions. I like the mnemonic, there's various ones, but oil rig, oxidation is loss of electrons, reduction is gain of electrons. So let's look at this in some chemical reactions here. Let's look at this zinc solid reacting with two aqueous protons. Zinc becomes then 2+, and you evolve some hydrogen gas. Okay, so let's go through and assign oxidation numbers to each element here, both on the reactants and the products. Zinc, an element by itself, elements are 0. Hydrogen, an element by itself, but it's an ion here, right, with a +1 charge. Okay, I'm not worried about the coefficients in front and determining what an oxidation number is. We will worry about these when we're balancing these types of reactions. But to assign the oxidation number, it's just +1 here for hydrogen. Zinc on the right becomes an ion of 2+, so that oxidation number is now 2+. And hydrogen, H2, elemental hydrogen, is 0. So zinc is going from 0 to 2+. It is losing 2 electrons. Its oxidation number is increasing. So zinc is undergoing oxidation, or it is being oxidized, losing those electrons. By comparison, hydrogen here, its oxidation number is decreasing because it is gaining electrons. Reduction is the gain of electrons. So hydrogen is being reduced. Now, we also have some what can be confusing terminology to refer to a reactant that is causing another reactant to change its charge. Okay, so since hydrogen here is being reduced, okay, zinc is the thing that is causing it to be reduced. So zinc here is the reducing agent, because it is the thing, the reactant that is causing hydrogen to be reduced. Likewise, hydrogen here gets a name. We call it the oxidizing agent. Why? Because it is the agent or thing that is causing something else to be oxidized. Zinc is being oxidized, so hydrogen here is the oxidizing agent. And frequently this will be the setup. The thing that is being oxidized is the reducing agent, and the thing that is being reduced is the oxidizing agent. So just keep that in mind. Okay, so let's now practice identifying the oxidation number of all the elements here in these reactions, and then identifying what is being reduced, what is being oxidized, and therefore what is the reducing agent and oxidizing agent in these reactions. And I'll just note again here that the agent sort of implies a reactant. Okay, like back here, we identified what was being reduced and oxidized, and then we said, okay, the reducing agent is the reactant here on the left side that is causing the reduction, and it itself is being oxidized. Okay, so just keep that in mind. Pause the video here and try to solve for these two reactions. What are the oxidation numbers? What is being reduced? What is being oxidized? And then what are the oxidizing and reducing agents? Okay. So we'll go through and identify the charge. The first one is pretty straightforward because it is similar to what we've done before on previous examples for zinc. Zinc goes from 0 to 2+. Copper is going from 2+ to 0. Okay, so 0 to 2+, it is increasing its oxidation number because it is losing electrons. Okay, whereas copper is gaining negative charges, gaining electrons. Reduction is gain of electrons to go from 2 plus, gaining 2 negatives to become a charge of 0. So here, zinc is undergoing oxidation, copper is undergoing reduction. Therefore, zinc is causing that reduction in copper. So zinc is the reducing agent. Zinc itself is going from 0 to 2 plus and being oxidized. Just to specify, zinc is being oxidized. It is the reducing agent, which is really what we were asked in this question, but we're just going to identify all of these terms here for these reactions. Zinc is the reducing agent. Zinc is being oxidized. Copper 2 plus is being reduced to copper solid with a charge or oxidation state of 0. And copper 2 plus is causing zinc to be oxidized. So copper 2 plus is the oxidizing agent. Okay, so those are my answers for the first one. For the second one, a little bit more complicated. Cadmium is an element, so that is 0, existing by itself, so oxidation number 0. Nickel oxide, well, we did this example earlier. Oxygen is -2, -4 total, so nickel has to be +4. Water, we talked about previously. Hydrogen +1, 2 of them. Oxygen -2, so those are the oxidation states there. Hydroxide, oxygen -2, hydrogen +1, for a total here of -1 in the OH group, and there's 2 of those. So -2 total, so cadmium here must be +2. And for the same reasons here, nickel will be +2 since oxygen is -2 and hydrogen is +1. Okay, so now that we have all the oxidation numbers written, we can come over here and identify that certain charges are changing. Cadmium is being oxidized, just like zinc up here. It's going from 0 to 2 plus. It's being oxidized. It's going to be the reducing agent, because it's going to be the thing changing its charge in order to cause something else to be reduced. So cadmium here is going to be our reducing agent. And I should probably be specifying like cadmium solid, for example. We can look at nickel going from +4 to +2. It is gaining 2 electrons. Right, +4 to +2. So it is gaining 2 electrons. Right? So nickel is being reduced. And I do need to be careful here and specify that it's the entire reactant here that is the reducing agent. Even though it's nickel itself that is being reduced, when we refer to an agent, it's the entire molecule, which didn't really come into play in these previous examples because all the elements were sort of by themselves. But here, we identify elemental nickel as being reduced. So the reactant that contains nickel, or nickel oxide as a solid, that is the oxidizing agent. Okay, so I wanted to do this one here. 2 examples. The first one kind of straightforward. The second one a little bit more complicated, but it also illustrates this last point that the agent here is the entire compound that has the element. If it's an oxidizing agent, It is nickel oxide because nickel is being reduced, and nickel oxide is the entire molecule that contains the thing getting reduced. Okay, so I think we'll stop this lecture here. Up next, we will talk about balancing redox reactions, which is what these reactions are. When something gets reduced and something else gets oxidized, we call that reduction oxidation reaction, or a redox reaction for short. And we need to figure out how to balance these, which will be much more difficult than just balancing normal chemical reactions. So that'll do it for this lecture. See you next time.